Okay, it's 5:30, so let's go ahead and get started. All right, good evening, everybody. How's everybody doing today? Good? Oh, it's good. You guys are in a much better mood than my undergrads. All my undergrads feel kind of beat up and exhausted at this point in the semester. So it's good that you guys are feeling good, or at least you say that you're doing good. But yeah, it's end of the semester. I know start of December now. So we're in December, so we're really getting near the end. So we have this week, we have next week, and then that's it. So we don't have a final exam in this class. We just have the final project. So I do want to take a little bit of time talking about the, just to kind of give you guys some hints on the final project today, because I have gotten a lot of questions the last few days, and so I just want to make sure that everyone's kind of on the same page, at least with just how to start part one, because I think there's some confusing variables that are there, and I want to make sure that you guys know how to use the connectivity and the nodes matrices, because those are going to be really important for the project. Okay. And then after that, we're going to be doing our ANSYS demonstration today. So. I'm not going to have you guys turn this in because I know the project's already going to be a lot of work. And so to do kind of another ANSYS activity, I think at this part of the semester, I think would be asking a little bit too much. And I think it would be splitting your guys' your time a little bit too much. But I want to make sure that you guys see this because it's a really important part of ANSYS, that will help you get around a lot of really difficult things. And so the theme, kind of building off of what we did on Monday, the theme of this ANSYS activity is, helping you how to mesh better. And so we'll be going over how to do beams and shell meshes today. And those are actually will help you out a ton for some really tricky geometries, okay? And so before that, I have one more announcement. So probably you guys got emails from the department already, but SOQs are available for this semester. So SOQs, that stands for Student Opinion Questionnaires. And so that's basically your guys' chance to, evaluate me on how this class has gone, okay? And so those SOQs are really important. So, I would, ask you guys definitely to fill those out. Not only are they used just for, for bookkeeping's sake, but, I do read really carefully, all the comments and the feedback that you guys give on those, because, end of the day, this is a job that I want to, constantly improving it. And I don't really, and it's really hard for me to get better without honest feedback from you guys. So, first of all, for anything, with that, remember that it's totally anonymous. So, I can't figure out who said what, but, I want you guys just to be honest with how this class went for you guys, especially this semester, which has been all virtual. So, it was weird in a lot of different ways, and I know that we had kind of a lot of, a lot of things that could have gone better too. So, please, anything that you feel like that could have gone better, or, any things that I did that weren't that good, please let me know, because, I really want to read those things and I really want to improve on them in the future. So, definitely fill those out. And I think you have until next Friday to do so. My recommendation would be to wait at least until our class next Wednesday to fill those out. Because I want to avoid kind of a Game of Thrones situation where, like, we get through the first 15 weeks of the semester, you might be feeling a certain kind of way, and then next week just might be a total train wreck, and you kind of wish that you didn't recommend it to all your friends or something like that. So I would say wait until we're all done. Wait until you see all the lectures, and then write those SOQs. As honestly as you can. Okay. Okay, are there any questions on any of that? I do want to go over the project a little bit. So if you have questions on the final project, maybe let's hold off until I go over that a little bit. But besides that, are there any questions I can answer right now? Okay. All right. So this is this is just a few just hints on the final project. Maybe not hints, but hopefully some information just to help you guys get started. Because the beginning part of this starter code is kind of a lot, and so I want to kind of make sure that we kind of go over together, what each thing is and what you should be looking for. Okay, so first thing I'll tell you is that this line right here is going to be really important. And so this line right here is the size of the elements in your mesh. Because right now, if you run this code, it'll error out, but it'll at least produce these 4 figures, which are really important. And what you'll see here is that, with the mesh size of 0.1, our mesh is kind of busy. There's kind of a lot of elements. And so it's kind of a little bit hard to figure out what's going on here. So 0.1 that's kind of a nice mesh element to kind of end up as, but when you're first working with the code and when you're first debugging, it'll really help to kind of increase this quite a bit. So let's increase this to 0.2, and you'll see that our mesh is a lot more coarse. And the nice thing about a coarse mesh is that you can actually read this mesh right here, which is usually nice. Okay? And so I'm going to focus a lot on figure 3 right here, because this is going to be one of the most important ones. And the thing with figure 3 right here is that it shows our mesh with all the nodes that are labeled. So you can see that everywhere that there's a vertex or everywhere that there's a node in the mesh, there's a number that's associated with it, okay? And so you can see here, let me see, how many nodes do we have? Number of nodes, we have 111. So there should be 111 of these guys, and they're numbered from 1 to 111, okay? And so this is really important because these are basically the nodal ID numbers or nodal indexes for our mesh. And so we use these node indices for a few different things. First of all, the reason we identify all of them with a unique ID number is so that we can kind of refer to them later, because we're going to need to pick out each one and know what their coordinates are and what the solutions are at those locations. So that's good. And we're also going to use them for another purpose, which is once we do the assembly for the global system, right? So remember, when we do assembly, we kind of pull all the element stiffness matrices together into one global system, and we need to know, which rows do we need to put, certain things, which rows and which columns. And so we're going to use the numbers here to kind of to specify which rows and columns, those entries go into the global matrix. So if we go, say, let's look at this this entry right here, N89, and so the solution and all this stuff for the global stiffness matrix, that will go in row 89 in there. So we're kind of leveraging the nodal ID numbers for both of those purposes. And this is pretty standard for a lot of finite element codes. And so for all finite element codes, basically, the mesher, which is what we're running right here, the mesher is usually in charge of assigning ID numbers to all the elements and all the nodes. And then the finite element code then uses that same numbering scheme for all of their internal algorithms. So we're kind of mimicking the same thing here. Okay. And so the first thing I want to go over are these two matrices right here. So the nodes matrix and the connectivity matrix. So you can see here I've created them using kind of some special functions from our mesh. Okay. And so remember, the mesh is already created for you. So I've already done that for you here. And then all I'm doing right here is kind of extracting some of the vital information that we need for the project. Okay. And so the first one is the nodes. So let's take a look at that one first. And so if we read kind of the tooltip for nodes right here, we can see that this nodes matrix contains all the XY coordinates for each of the nodes in the mesh. Okay. And so if we go into our workspace here, and we go to the nodes matrix, which is right here, we can see from this tooltip right here that it's a matrix that's two rows, and it has 111 columns. Okay. And so what you're seeing right here is that for each column here represents each column represents the X and Y coordinates for each of the nodes in the mesh, okay? And the column basically tells you which node ID that it's in, right? So if we go back to our figure here with the node IDs, and let's look at column number 65, right? And so let's find node number 65. And of course, I picked one of the most random ones here. So it should be somewhere here, 65, right here. Okay, and so for node 65, the XY coordinates for that are going to be the X coordinate is going to be 0.2174, right? And so the nice thing here is you can see the coordinate axes, and then the Y coordinate is going to be 0.4977. So you can go and see that it's approximately 0.5, which is right there. Okay, and so this is going to be important because we need to know the physical coordinates of each node in order to use them in our algorithms. Okay, and so that's the nodes matrix. So remember, the way that we're going to use the nodes matrix is we're going to specify the row to be either 1 or 2. And so a row of 1, if we specify the row at 1, that means that's going to be the X coordinate. And then the second row is going to be the Y coordinate. And then the column that we choose is going to be the nodal ID number. So I'm going to implement basically this part of the code right here for you, just to kind of show you what I mean by that. Okay? And then the second matrix here is the connectivity matrix, okay? And if we read the tooltip for the connectivity matrix, we basically see that this array holds the node indices that are connected to each element, okay? And so let's go ahead and open that. And so we have this right here, okay? And so connectivity, if you kind of remember back when we did our frame code, remember when we did our frame code, you know, for each of the frame elements in our structure, we need to know which nodes that they were connected to, right? And so this is kind of exactly the same thing, except now our elements have 3 nodes because our elements are triangular, right? And so the way to read this matrix is that the number of columns here indicate the number of elements in our mesh. And so in this particular case, we have 180 elements. And so if you count the number of triangles here, there should be 180. You don't have to do that. You can just trust MATLAB to know that what it's doing, okay? And then from there, you know, what these are showing you right here are the nodal indices or the nodal ID numbers for those, for that triangle. And so let's see if we can find this one. So node 68, 66, 68, and 21. So it should be somewhere around here. Yeah, actually that's this element right here, okay? And so if we kind of zoom in on this triangle right here, we can see that the 3 nodes that are connected to it are nodes 21, node 66, and node 68, okay? And so that's what's given here. So the element with index 1, so element 1 right here, has nodes 21, 66, and 68 connected to it. You know, and that's what's represented here in the connectivity. So you can visit basically every single element here, and that's actually what we're going to be doing in the next part, and then use that information to obtain, you know, the correct nodal information, most notably the correct nodal coordinates. Okay. All right. Any questions on these two so far? Okay. Yeah, so I wanted to make sure I go over this because these are probably the 2 most important data pieces that I give you. And hopefully most other stuff is fairly self-explanatory, like the number of nodes, number of elements, K global, F global, K element, F element. So all of that we've kind of seen before. Okay, I'll leave this part to you. So from most of what I've seen from people who have reached out, most of you guys are filling this out okay. So you know, I'll leave that to you guys. But basically, these are just the Gauss points for a 3-point triangular element. So I think we went over that at the very end of the lecture notes 12. Okay? And now let's fill in this part right here. Okay. All right. And so in this part of the code, what we're doing is we're looping over all of the elements in order to compute our element stiffness matrices. Okay. And so in this first part of and so that's what this loop is right here. So we're doing a for loop where our loop index is I_e, and we're looping over all the elements. So you can see right here, what we're doing is we're visiting all the elements in our mesh. So that's very similar to kind of what we've seen in our previous codes. Okay, and so the first thing we need to do is we need to obtain the nodal indices for each element. Okay, and so basically, once we visit each element, we need to know what the node ID numbers are for each one. Okay, and so say that, you know, we're starting with this element right here, and so if we're visiting element 1, N1 needs to be I'm actually not sure what order they pick, but let's say that N1 has to be 21. N2 has to be 66, and N3 has to be 68, but the order might be different. Actually, you know, it'll actually follow this order right here. Okay. And so the way that we're going to do that is we're going to use our connectivity matrix. Okay. And so N1, which is the index, the node ID number for node 1, we're going to do connectivity. Okay. Our connectivity has 3 different rows, so N1 is going to be the first row in this one. So do connectivity 1. We're going to, for the second entry, we're going to put the element ID number, which is I_e. Okay. And so what that'll give us basically is the first nodal index for the node in that element. Okay. And then we can just kind of copy this down for the rest of these guys. Okay. Right. And then for N2, we're just going to switch over to the second row. And then for N3, we're just switch over to the third row. Okay. And so with this, we basically obtain this information here that's in our connectivity matrix. And so now that for each element that we visit, we know what their global ID numbers are, and we can use that to access some other information. Okay. Okay. And so some of that other information that we need is going to be the nodal coordinates. Okay, and so if you kind of reference this with our notes, this is going to be the code to obtain x1, x2, x3, and then y1, y2, y3. Because before we do anything with the element stiffness matrix, basically in order to compute the Jacobian, we need to know the physical coordinates of each of the different nodes. Okay, and so in order to do this, we're going to use our nodes vector, right? Okay, and so x1 right here is going to be the physical x coordinate of the first node. Okay, and so if we go back to our nodes matrix, okay, we know that the x coordinate is given by the first row, so we're going to put a 1 right here. Okay, and then for the column, we want to specify the correct node, the correct column that specifies to the first node. Okay, and so we're going to put n1 right there. Okay, and so what this will do is this will obtain the x coordinate for the n1 node in our matrix. Okay, or in our mesh. Sorry. Okay, we can do the same thing here. Okay? And so for y1, we want the y coordinate for the first node in our mesh. And so we're going to, once again, call the nodes matrix. But instead of the first row, we're going to go to the second row, which our second row is our y coordinate. And then we're going to go to the n1 column, whatever that happens to be for this element. Okay? So let's say that we're visiting element 1. So element 1, we're going to go to the 66th column of nodes. Okay. And so x1 is going to be 0.3017, and y1 is going to be 0.1554. And so we go to our mesh, we go to node 66, right? Node 66 is right here. And we can see that the x coordinate for that's going to be 0.3017, and the y coordinate 0.1554. Okay. And so with the code written like this, you'll obtain all the x and y coordinates kind of automatically, you know, and you can fill in, you know, the code for x2 and x3. Okay? And then once you have that, you can put them into a single matrix like this. So this is, I think in the tooltip we say it should be a 3x1, and so we'll do x1 semicolon x2 semicolon x3. And so this is basically the x coordinates for each of the nodes in that triangular element, kind of stacked all on top of each other. Okay, and then from there you can kind of put things into different matrices just to organize them, and then from there you should be good to go in order to compute this. So once you kind of deal with those data entries and you know what the coordinates are, from here you can just follow the same algorithm that we've done in class. You know, for how to do isoparametric elements, except this time you're doing it for a triangle. Okay. Okay. Any questions on any of that? Okay. All right. So hopefully that clears some things up. I know the nodes and the connectivity matrices were a little bit you know, confusing when you're first looking at it, but I think once you kind of understand what those matrices do, then the code becomes hopefully a little bit easier to work with. Okay. Okay. And so that's all I want to say for the project for now. And so let's move on to our ANSYS demonstration. Okay. Okay. So remember this ANSYS activity. I say it's optional, but I'm not even going to collect anything for it. So you know, you guys can kind of just sit back and watch if you want, because you know I want to make sure that you know you guys see you know some ANSYS stuff, just because you know that's kind of a big part of finite elements. But I know that you guys already have a lot on your hands with the final project. So that's kind of why I chose to kind of take this route right here. Okay. Okay. And so the title for this ANSYS activity is A Bridge to New Element Possibilities. So I'm a sucker for kind of punny names and kind of lame dad joke names. So the geometry for this is actually going to be a bridge. That's why hence the name. Yeah. These jokes are not as fun when you guys aren't in the same room. Okay. Anyway, so the whole theme for this this activity here is to basically just to introduce you to different element types. Okay. And so at the end of lecture on Monday, we went over kind of the two most common element shapes for 3D finite element analysis. So we went over the tetrahedron, which is the four-sided pyramid, and we also went over the hexahedron, which is our brick element, right? And so those will serve you well for a lot of different geometries, right? And since these elements here are three-dimensional objects, right? So they actually have 3 dimensions. Another name for these type of elements are called solid type elements. So you'll hear that term often in the you know, in industry. And so when people say, you know, this element is a solid type, all they mean is basically it's just some three-dimensional object. Okay, and the main ones are tets and hexes. Right? And so these will serve you well. So these will work great for a lot of geometries. But you know, where it really works well is when, you know, your object has relatively the same lengths in each of the three coordinate directions. So the length in the x direction, the length in the y direction, and the length in the z. If all of those are approximately the same, then you know, then your solid type elements will work really well. And the reason for that is because it's, you know, because these are three-dimensional objects. If you have a three-dimensional space or another three-dimensional object that's kind of relatively solid type, then it's easy to kind of fill the space in with kind of smaller three-dimensional objects. And so that usually works pretty well. Okay? And so where this usually fails is if your geometry has one or more length that's significantly less than another one. Okay? And so what I mean by that is if your geometry is either thin or it's really slender. Okay? And so if we look at our bridge geometry right here, you can see we have most of the geometry here is actually either thin or slender. Okay? So if you look at kind of the sides of the bridges right here, you know, if we kind of take this entire kind of semicircle as one piece right here, and so the length of this and the height of this, the length and height of this semicircle piece are at least roughly the same order of magnitude. They're not quite the same, but you know, but they're at least comparable, right? If you compare that to the thickness of this semicircle, you can see the thickness is way smaller than the length and the height, right? And so that's going to present some challenges with the mesh because it's you know, when we try to fit some tets and some hexes in there, you know, it's you know, it's going to be a bit more difficult. Okay. And so I've kind of given you kind of an example here of what that tends to look like. So if you have kind of an object where, you know, it's relatively thick in all directions, then it's kind of really easy to pack it together with elements. Okay, so you can see here that, you know, we have a roughly equal number of elements in each direction, which is good. Okay, but if you have a geometry here that's either thin or slender, what can tend to happen is that your elements will only be kind of one across like this. Right? So you basically what we call this in the industry is you only have one element through the thickness. Okay, and so this is typically really bad because what you have here are, you know, all the nodes are existing just on the edges. Okay, and the edges are usually where you apply boundary conditions. Okay, and so if you don't have any nodes or you don't have very many nodes on the interior, then what can happen is that your solution can be pretty poor quality. Okay, and so when you have these thin and slender geometries, you know, it's usually very difficult to mesh them and get you know, reliable solutions. Okay, at least with solid elements. Okay, and so this is especially bad if you're doing like structural finite elements where you're interested a lot in kind of the stresses. The mechanical stresses. So in those cases, you know, having only one element through the thickness will give you really inaccurate results. Okay? And so one way to solve this is you can just simply refine the mesh. And so in the industry, we call this meshing the shit out of it. And so basically we can just refine the mesh enough or make the element small enough such that, you know, you achieve kind of the same thing here, where if you have kind of a thin element or thin part of your geometry, if you use kind of small enough elements, so say all the elements are kind of this size right here with this box, then you can get enough of them to kind of get enough through the thickness, and that works. You know, I'm not saying that's a bad thing, right? But the problem with that is, you know, if you kind of you know, mesh the shit out of it, then you have so many elements here that, you know, the cost of your simulation just becomes way too high, right? Because we know that, you know, more elements means more nodes, and more nodes means a bigger linear system, and that's usually not that good a thing. Okay. And so, you know, besides, you know, refining the mesh to some impractical amounts, another thing that you can do is you can use different element types. Okay, and so it turns out since having thin and slender geometries are very common in practice, you know, there's been some specialized element types that kind of fulfill this purpose, that let you mesh it more efficiently. Okay, and these element types are called shells and beams. And so these are actually 2D and 1D elements, respectively. So, you know, even though you're doing a three-dimensional simulation, you know, your elements can still be 2D and 1D. And these actually, you know, help you quite a bit. Okay, because now instead of trying to you know, try to fit in a bunch of really, really small solid elements to a thin space. You can instead just replace it with a layer of 2D elements, you know, and that's going to be a lot more efficient. Okay, and the reason that these guys are a lot more efficient is that they also compute rotations at their nodes in addition to the displacements. So it's actually, you know, it's actually pretty nice that in this class we went over beam and frame elements at the beginning of the class. Because remember when we did that, we computed not only x and y displacement, but we also computed the rotations, right? And so that's kind of what these 2D and 1D elements do as well. So that they, in addition to displacements, they also compute rotations, and that actually helps you, you know, quite a bit. Okay, because from there you can compute stresses, you know, a lot more accurately than if you just had displacements there. Okay, and so of course, you know, this is talking just within the context of structural mechanics, but these element types actually exist for other physics as well, right? And so you can one example that comes immediately to mind is you can have 1D element to represent fluids actually, and so I've actually, you know, I personally haven't worked with it, but I've seen other people work with it where, you know, if you have just, you know, flow in a pipe, you can instead replace that with just a line, right? And then you can solve for, you know, the flows and the pressures in that pipe in the same way. And usually you can do so a lot more efficiently if you try to fill that pipe with 3D solid elements. Okay. And so that's going to be the focus for this activity. So the focus of this activity is how to take a 3D geometry and how do we convert it into something with beams and shells, so that we can mesh it more efficiently. Because this geometry that we have right here, normally this would be very difficult to mesh because we have a lot of thin and slender geometries. But if we switch to shells and beams, you know, it'll be actually a lot more easy to mesh. Okay. All right, any questions on this? Yeah, it's a good point, Chris. Yeah, so probably only works with pathline graphic in post-processing. Yeah. So you will need some additional kind of post-processing to do that, but it's for most cases, ANSYS kind of has those kind of built in for you, so you don't have to worry about that too much. All right, any other questions on this before we move on? Okay. So if you want to follow along with me, I did upload the PDF and the CAD file for today. And so if you go to our course website and you go to week 15, sorry, then you can download the PDF here, ANSYS activity beams and shells, which is the PDF that we were just looking at. And then this bridge geometry right here, this is the CAD file that we're going to use. Okay. So if you want to follow along, you can download those things. But if you just want to sit and watch, that's totally fine too. Okay. All right, and so in order to do this, we're going to use a side of ANSYS that we haven't seen before, which is the Spaceclaim program. Okay, so Spaceclaim is kind of the CAD software, one of the CAD softwares that comes packaged with ANSYS, and it's actually, you know, helps us to get this geometries pretty well. Okay, and so here's a summary of what we're going to do. So we're going to open up a geometry in Spaceclaim. We're going to create shells. We're going to create beams, and then we're going to mesh and run this in ANSYS. Okay. Okay. And so the first step is we're going to load our CAD geometry. So if you're following along, you can download the file, and you should see that it's an IGES file or IGES file. So go ahead and download that, and then let's open it up in ANSYS. Okay. Okay. So from here, I'm going to start to go to ANSYS. Right. And so for this simulation, we're going to do a structural simulation. So let's click and drag static structural, and then let's put it into this area right here. Okay. And then let's load in our geometry. So let's go ahead and right-click geometry. And let's go ahead and import data. Okay. And so I have it here on the shortcut, but for you guys, probably you'd have to browse and you'd have to go to the right location. So let me go here. ANSYS, bridges.igs. Okay. Okay. And so from here, we need to work on this geometry a little bit before we can actually simulate. So let's go ahead and right-click geometry. And then let's click Edit Geometry in Spaceclaim. Okay. Oh, yeah, that's a good point. Yeah, so Chris made a great comment here. So if you are using ANSYS Spaceclaim, this actually lets you modify your geometry. whereas the other CAD software, design modeler, doesn't allow you to do this. So, you know, if you have a situation where you have a CAD and you need to modify it a little bit for simulation, Spaceclaim it should be your go-to tool. Yeah, great point, Chris. Okay, and so after a little bit of loading time, hopefully you should be able to see this. Okay. And if you want to kind of fly around the model like this, what I'm doing is I'm basically clicking. I have a mouse, and I'm basically clicking on the middle of the middle button or the mouse scroll, and I'm kind of moving it around. Okay. Okay. And so the first thing that we need to do is, which is kind of good practice if you're using Spaceclaim, is to kind of clean up the geometry if you can. Okay? Because sometimes, and for this case especially, because I got this geometry from GrabCAD. And so someone was nice enough to CAD this up and put it on the internet. And as just a resourceful person, I went and got that geometry. So full disclosure, so I didn't make this, right? And so anytime you bring a geometry into here, you know, it's a good idea to kind of clean it up a little bit. Okay? And so we're going to be doing a lot of manual things to clean this geometry up, but there's some things that, but there's some automated tools we can take advantage of first. Okay? And so to do that, you know, once you open up Spaceclaim, you can go ahead and click Repair right here, okay? And then under Repair, we're going to click these two buttons right here. So first thing we're going to click is Stitch, okay? And so what Stitch will do is that if there's any kind of errant edges or edges that they think, you know, should be connected, it's going to basically stitch those together. And so in this case, there are no stitchable edges. But if there was something that could be stitched, this green check mark right here would be ungrayed out. And so what you can do from there is you can basically just click this. You just keep clicking it until it grays out, and it should automatically fix some of those. Okay? And so that's kind of a nice feature for Spaceclaim, so that it can kind of automatically see what some problem areas might be, and then just kind of fix them up for you. Okay? And so the next thing that we can find out is any gaps in the model. Okay? So any gaps is basically anywhere in the model where, you know, there are two things that should be meeting that don't. And so so you can see here we have one gap that Spaceclaim found, and then you can see it's highlighted in red right here. And so to fix that, we can just click this green arrow right here. Okay. And so usually when you click that, you know, the problem areas will automatically get fixed. But because this model is a little bit special, then this problem area wasn't fixed right here. Okay. And so that's okay. So, you know, just because we have a problem area here, you know, we can kind of fix this later. But I'm showing this to you guys just so that, you know, if you are bringing a geometry in, you know, you want to kind of run these tools first just to kind of try to clean things up. Okay. Okay. And so our next step here is we're going to basically turn our thin entries here into shells. Okay. And so basically the parts of the geometry here that basically looks like it could be replaced with a thin sheet or a thin sheet of paper, we're going to go ahead and do that. And so in this model, we can see that we have kind of three such features that can be turned into thin sheets. Okay? And so the first thing that we have is the road itself. So you can see the thing in black. And so you can see here that it's very thin. Okay? And so if we try to mesh this with either tetrahedral elements or hexahedrons, you know, it's really going to struggle to do that because this guy is so thin. Okay? And so what would be better is if we replace this, if we just simply replace this with a two-dimensional sheet. And so the other ones that we're going to use for this are going to be the arches right here. So you can see these arches are also fairly thin. And so if we replace this with kind of a thin sheet, then that would be kind of more efficient to do that. Okay. Okay. And so in order to do that, we're going to use an operation called a midsection. Okay. And so if we go back to the top of Spaceclaim right here, we can see that there's a tab called Prepare. So let's go ahead and click that. Okay. Or mid surface. I'm sorry. Yeah, it's always mid something. Okay. And so let's go ahead and click this button here for mid-surface, right? And so now what we need to do is we need to select the parts of the geometry that we can mid-surface, okay? And so the way that this is done, as you can see, as I'm mousing over certain things, you know, things are highlighting yellow. And so the way that this works is that we need to make two clicks. And so the first click that we need to make is the first plane for our midsection. So let's go ahead and click this road, okay? And so you can see it's a little bit hard to tell, but the top part of the road here has become selected. And then we need to click the road again, which will select the bottom surface of the road. And then that will form our two planes for the midsection. Okay? And so you can see from our camera right here that, you know, I'm kind of rotating back and forth, that the top of the road is highlighted in blue, and the bottom of the road is highlighted in green. Okay, and so what Spaceclaim is going to do now is that it's going to create just a 2D plane that's going to be right in the middle of these two guys. Okay, so let's go ahead and click this green check mark, which will go ahead and create that plane. Okay, and so you can see here that you know, the original road here was kind of grayed out, so you can see it's a little bit hard to tell, but the black parts here, the black transparent parts, that's what the road used to be, and then this blue plane in the middle, that's the midsection that was created. So let's go ahead and click away, and you can see here that instead of our thin road, which had a thickness, now we've kind of replaced this with kind of a sheet of paper, you know, to kind of represent that road. Okay, and so what this will allow us to do is that when we bring this over into ANSYS Mechanical, when we mesh this guy, then ANSYS is going to know to use 2D element types. And so it knows to, you know, now that we have this kind of paper thin structure right here, it's going to use triangles and rectangles to mesh this instead of tetrahedrons and hexahedrons. And so that's going to be a lot more efficient to do so. Okay. Okay. Any questions on this? Okay. All right. So let's do the same thing for the two arches. So we let's go ahead and we're still under mid surface here. And so let's go ahead and click this interior side of the arch, and then let's go ahead and click the back side. Okay, and you can see the same thing. So we have one part highlighted in blue, one part highlighted in green. And go ahead and click the check mark, click away, and you can see now that we've replaced the arch with kind of a thin, paper thin, you know, shell. Okay, and then finally, let's do the same thing for the other arch. So let's go ahead and click this, click the other side. Click OK. And so you can see here now we've replaced the roads and we've replaced the arches with shells. Okay. And so now when we bring this into ANSYS Mechanical, you know, we're going to mesh this guy with 2D elements. Okay. And that's going to be a lot more efficient. Okay. And so those are shells. And so anytime you have kind of a thin aspect to your structure, you know, shells are a great way to make it easier to mesh. And so now let's go over beams. Okay. And so you can see here we have a lot of geometries here that would work well for beams. So in this case, we have actual literal beams, and so we actually have, you know, structural elements here. But anytime you have a you know, a part of your geometry which is, you know, has one length that's much longer than any other dimension. So you can see here this is much longer than it is wide or tall. Right? Those types of geometries there are great for beams. Okay. And so to get beams, we're going to use this tool right here. And so we're going to use extract. Okay. And so we'll go back up to this prepare tab right here and click extract. And then from here, we can go ahead and click all the beams here. Okay. So we can see once I click that, it replaces it with simply a line. And so let's go ahead and click all the other beams on the bottom right here to replace them with lines. Okay. Doop, doop, boop, 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 and boop. Okay. And with that, you know, that's all we got to do. So it's you know, it's relatively simple. So it's nice that Spaceclaim kind of can automatically determine, you know, that this is a thin structure and we can replace it with a beam. And so beams, you know, ANSYS is going to mesh these guys with 1D elements actually. And so if we kind of go back, you know, a little bit farther in our class, you know, 1D elements were just kind of our line segments here. And so ANSYS is basically going to mesh this with line segments to, you know, and that's going to be a lot more efficient than trying to jam, you know, tets or hexes in there. Okay. Okay. Any questions so far on how we did mid-surfacing and extracting? Question? Yeah, that's a good question. So, so the question in the chat is, what is the reasoning behind not using tets or hexes for the beam parts? And the reason for that is, you know, kind of go back to this geometry here. And so if you can imagine, you know, if we try to put like let's say that we try to put tetrahedrons in for this thin beam right here. And so you can do that, but unless you pick a mesh size that's really, really tiny, what's going to happen is that, you know, you're going to have your tetrahedral element is going to span the entire cross section for this beam right here, right? And so we're basically going to run into this issue right here, where our geometry has only one element through the thickness. And so these are situations that we want to avoid, because in these situations, you know, all the nodes in that element are going to be on the exterior of the mesh, right? And the thing with the exterior is that, you know, those are boundary nodes. So those are often treated differently than interior nodes, because either we're applying boundary conditions on these guys, or they're, you know, or they have some other thing that's applied. So when you're trying to compute things like stresses, or you're trying to compute kind of more derived quantities, if you have only one element through the thickness, that leads to some really inaccurate results. And so, you know, if just to kind of give you an example, if we had kind of a beam like this, and say that we applied kind of a vertical force right here, where we put this in bending, and we wanted to compute, you know, what are the structural stresses, you know, the normal stresses, von Mises stresses, you're going to get a pretty bad result for something like this, because you don't have any interior nodes. And so the thing is, if you replace that beam with a, if we replace this with a 1D beam, then what ANSYS can do is that it can also compute rotations at each of those nodes. And that helps a ton, because then we can compute stresses and things a lot more accurately than if we than otherwise not. Right. Does that answer your question on that? Great. Yeah. So it's a little bit hard to kind of because you know we can go into a lot more detail about why this is bad right here, but it kind of gets into the weeds of kind of you know, a lot of messy math. So. You know, I know it's a little bit of a hand wavy explanation, but it's but you know, it's typically that's kind of what you would want, is you want more than one element through the thickness. Okay, so let's come back here. Oops, wrong one. Okay, so now that we've converted everything to shells and beams, you would think that we're kind of done at this point. Unfortunately, that's not the case, because you can see, you know, if we kind of zoom into this part of the structure right here, you can see that because we've kind of eliminated thicknesses in our model doesn't connect in the same way that it does. You can see that we have kind of a gap in between where this beam ends and where this shell thing starts. And so that's bad. So that's we don't want any gaps in our model, and we certainly don't want things to be floating around like this. We want things to be kind of appropriately anchored. And so we need to actually you know, make sure that these guys connect. And so thankfully, you know, Spaceclaim has a tool to do this, and it's going to be the extend tool. Okay. And so if you kind of read the tooltip for extend right here, we can see that extend surfaces or edges in order to make sure that they intersect with another body. Okay. And so we basically want to extend all of these guys right here to make sure that they intersect properly with other parts of the geometry. Okay. So let's go ahead and click extend. And when you first click extend, you probably get a tooltip here that said no areas found. Okay? And so basically it's saying that I can't find any places where I can extend, you know, and be okay. And the reason for that is because there's a setting here on the left-hand side for how far that we can extend. So the default here is 10 millimeters. And so what Spaceclaim is looking for is are there any 10 millimeter gaps in our model right now that we can cover up. Okay? And so sometimes what you're going to need to do is you're going to need to increase this quite a bit. And so for this particular case, let's change the maximum distance to 50 millimeters. Okay? And so what this will do is it'll look for any gaps in your model that are at least 50 millimeters, and then it'll try to connect them. Okay? So once we change to 50, we can see here that a lot of places are lighting up now. So you can see all of them are highlighting in red. Okay? And then all we have to do at this point is just click this green check mark, and it'll automatically connect these parts together. Okay, sometimes you might have to click it more than once. So in this case, I had to click it twice. And so once I did that, you can see here now that this beam extends all the way to this to the shell element right here. And so once we do that, now we can do this. Okay, so that's all well and good, but you can see here that it didn't work for all of them, right? And so you can see from the bottom here. Let's go from the bottom up. And let me turn off this this surface right here, just so you can see a bit better. Okay. You can use this this menu right here to turn off the visibility, just to help you see a bit more. Okay, so all I did right here was I just turned off the road. It's still there. I just made it invisible for now. Okay. And so if you kind of look at the bottom here, we still have some beams here that are not connected to the structure. Okay? And so that's a little bit troubling, because you know the extend tool should have caught these guys. Okay? And the reason it didn't catch it I think it might be easiest to kind of view it like this. Okay? So it's a little bit hard to see, but you can see that there's kind of a dot right here. So that's our beam, right? And we want this beam to be connected to this this planar structure right here, right? And so when we can view it from this plane, we can see, and we can zoom in, that this beam, you know, just by the nature of creating our beam element, is kind of below our bridge right here. Okay? And so basically, what Spaceclaim tried to do is it tried to extend this beam out this way, right? But it found nothing to connect to because this beam is a little bit too low, right? And so what we need to do actually is we need to actually raise this beam up a little bit and move it up such that it's actually, you know, within the same plane or above this bottom edge right here, and then we can properly extend it. Okay. And so in order to do that, we're going to use two tools in Spaceclaim. So we're going to use the measure tool, and then we're going to use the move tool. Okay. Because first we got to find out how big this vertical gap is, and then we need to actually move this up, you know, by this certain amount. Okay. And so let's go back up to this top menu right here. So let's go ahead and click measure. Okay. And then let's click this measuring tool right here. Okay. And so what this measuring tool would allow us to do is it allows us to measure certain things. Okay. And so before we do that, I'm going to turn on this option right here called show XYZ vectors. And what that'll do is it'll allow us to basically show kind of the XYZ distances in between certain things. Okay. Okay. And so from here, what we can do is we can basically hold control and then click our two different things. So let's go ahead and hold control and click our beam. And then let's hold control and click our bottom edge right here. Okay. And then from here, we can kind of see what the distance is. So, oops. And so from here, we can see that the Y distance in between this beam and this bottom edge is minus 0.4127 millimeters. Okay? And so in order to actually run a simulation with this beam, or in order to actually connect this to our structure right here, we need to move it up by 0.4127. Okay? All right, so let's kind of remember that number in our head. Actually, let me punch it in right here. Okay, and then now let's actually move this beam up. Okay, so this goes back to the comment that kind of Chris made at the beginning of lecture today, or you know, when we opened up Spaceclaim, that you can actually use Spaceclaim to modify the geometries, and we're going to use that in this case here. Okay? And so to modify the geometry, let's go ahead and click Design, and so that'll open up a new tab here. And then let's click this button right here for Move. Okay? And so from the tooltip here, you can see that Move will allow us to move certain objects in our geometry just by simply clicking and dragging. Okay, so let's go ahead and click Move, and then let's go ahead and click this beam. And then once you click the beam, you can see that we have arrows that appear here. And since we want to move it vertically up, so we'll click this this blue arrow right here, and we'll just kind of slightly drag it up right here. Okay, so you can click and drag this to any length, but once you do that, you can actually enter the number right here, which I think is kind of the most convenient. And so let's move it up 0.413 millimeters. Okay, and so what that should have done is that now this guy should be in line with this structure. And so if we go back to the Prepare tab, and then we click Extend, where'd it go? Right here. We can see now that ANSYS has found two areas where we can properly extend this beam. So let's go ahead and click this green check mark, and we can see now that the beam is now properly connected to the bottom structure. Okay. All right, so we're going to need to do this for. Looks like we have 3 more beams that are not connected properly. But before we do that, or I guess as I'm doing that, are there any questions on what I did there? Question. All right, so the question is, looks like the beam also needs to move in the X direction, but the X was 0 before. Yeah, that's a good question. So the X direction, you know, for that we allowed the extend tool to kind of handle that. So you're right. You know, the beam did need to be extended in the X direction in order to, you know, or I guess in this case it's the Z direction, in order to meet the plane here. But we let the extend tool basically do that because we're actually kind of extending the length of this beam in order to meet this structure right here. So that's usually better handled by the extend tool. So the only thing that we did basically was just to make sure that the two are kind of in line with each other, so that when they extend, they actually intersect. Yeah. Okay, and so when we do the same thing here, when we click measure, we can see that the distance here is minus 1.8987. So let me punch that in here. Okay, and so we're going to move this guy up just a little bit. Okay, okay, so let's go ahead and click away, click design, click move. Okay, let's click this guy, and we're going to move it up. Okay? And we're going to move it up 1.899. Okay, and then once we do that, we're going to go ahead and click prepare, extend, and then extend this guy right there. Okay, and so that's 2. Okay, so now let's move this guy. Measure. First, find out how much we need to move it up. We can see here that the y displacement here is 1.497 or 4.4797. Okay, and so let's move this guy up 1.48. Okay. Okay. Let's go back to prepare, extend. 3 areas. What? Okay. It's weird. Should only been 2. Oh well. Okay, and then now let's do the last one. Okay. Okay, and so you can see the vertical displacement here is 1.9221. So let's move this up 1.93. Let's go ahead and hit extend. Okay. All right. Oh, one more. Okay. All right. And so now that we've done all that, you know, all the beams are properly connected, so we're looking good. And so the last thing that we need to do is we need to make sure that the road connects to the sides as well. Okay. Okay. And so the road kind of has the same issue. So we want the road to be sitting on our beams on the bottom, because those are, you know, what the beams are there for. But you can see here that the road is kind of floating up quite a bit. Okay. And so we're going to do the same thing where we're going to, you know, move the road down such that they're connecting, and then extend them to make sure that the road kind of hits the sides of the bridge. Okay. So let's go ahead and use our measure tool again. So let's measure between the road, and then let's do the bottom edge here. Okay. And we can see that this distance right here is 28.3735. Okay. And so that means we're going to move it down by an amount of 28.37. So you can see that's quite a vertical drop, but now you can see it's basically right on top of all of our beams. Okay, and then what I'm going to do, another thing I'm going to do is I'm going to connect this left edge to the right to the sides, and then from that we can use our extend tool again. So you can see when we did extend, we found 2 problem areas. We just click the check mark, and now we've connected the roads there. Okay. Okay. So that was quite a bit of cleaning up to do, but now we have a model where we've replaced all the solid parts of the geometry with shells and beams. Okay, and so when we mesh this guy, it's only going to use 2D and 1D elements, you know, which are going to be much more efficient for our you know, for our simulation. Okay. Are there any questions on this before we move on to ANSYS mechanical? Okay, and so since we're done here, we can just simply close this window. Okay, and then we'll double click model right here to open this up in ANSYS mechanical. It takes a little bit of time to attach the geometry. Okay. And so, oops. Okay. And so now that we've have our geometry here, we're ready to start working on it. Okay. And so one kind of weird thing with this model in particular, hopefully you don't have this, is that we have this kind of weird surface right here. So remember before when we had that thing that couldn't be fixed with the gap, you know, that's this kind of weird toothpick thing right here. So, you know, it's not really contributing anything to the simulation. So we're just going to go ahead and just kind of get rid of it. And so in order to get rid of a certain geometrical aspect, you're going to right click it here and then click just suppress geometry. Okay. And now it's out of sight, out of mind. So it's, you know, like we swiped it under the carpet and now we don't have to worry about it. Okay. All right. Okay. So the first thing that we need to do, actually before we mesh, is we need to add our proper constraints here. Because you can see here we have a lot of different aspects of the geometry, and we need to make sure that they're connecting properly. Because we just spent all that effort kind of making sure things connect, and we want to make sure that ANSYS knows that they're properly mated to each other too. Okay. And so to do that, we need to add what's called connections. Okay. And so connections is kind of ANSYS's way of telling, or it's your way of telling ANSYS how different bodies in your geometry are going to interact with each other. Okay. So let's go ahead and right-click connections, and then we're going to need to insert a manual one. So let's go ahead and right-click connections, insert, and then manual contact region. Okay. And then from here, we're going to select two aspects of the geometry to mate with each other. Okay. And so the first thing that we're going to do is I'm going to mate all these beams to the left support right here. Okay. All right. So the first thing I'm going to select is just this side of the bridge. Okay. So to do that, I made sure I was in face selector mode, and I clicked that side. And then on this part right here under contact, I'm just going to hit apply. Okay. Okay. And then connecting to that are going to be all the beams. So, you know, the beams, they're only going to connect at a point. And so in order to do that, I'm going to click point select mode, so vertex mode. Okay. And I'm going to select all of these connections right here. So I'm basically going to click this, hold control, and then click all the other locations here. So I didn't miss any, right? Okay. And so once you've collected all those, go ahead and hit apply right here. Okay. And then we've successfully bonded these. Okay. Sometimes you might get an issue where, like, after you've selected the two bodies, you know, it's going to complain about it. So you have this question mark right here. Sometimes all you have to do in there is you just have to kind of flip the order. So if you right-click this this connection right here, and you see that things are still yellow and you have this question mark, sometimes you click this, you flip it, and then now it's suddenly okay. Okay. And so, you know, if you're trying to make connections in your ANSYS geometry and it's all yellow and question marks, try flipping it. Try flipping the order, and then that might help you. Okay. I'll be honest, I'm not exactly sure why that helps, but it's it works for me. Okay. Okay. So let's go ahead and do this for the other side now. So let's go ahead and right-click contacts, and let's go ahead and insert another manual contact region. Okay. And let's do it in the reverse order this time. So let's go ahead and click all the vertices on this side. So make sure we're in vertex select mode. Okay. And then let's select all these points right here. Okay. Go hit apply. Oops, I missed somebody. Missed this guy. Okay. And then now for the other one, let's select the left plane. So let's go ahead and click that. Hit apply. Okay. And so now all our beams are successfully mated to the sides of the bridge. Okay. All right. So the next thing that we need to do is we need to make sure that our road is mated together with the supporting beams on the bottom. So let's go ahead and right-click this and insert another manual connection region. Let's go ahead and select the road, and that's going to be the first one. Okay. And then we want to select all the beams. So the beams are all just edges. So we're going to make sure we're in edge selector mode. We're going to click all of the beams here. Okay. Let's go ahead and hit apply. Okay. So you can see ANSYS doesn't like that, so we're going to flip it. And then now we're all good. Okay. Okay. And so the last thing that we need to do is we need to make sure that the road is connected to the sides of the bridge right here. Okay. And so specifically, we want to make sure that the edge of this road right here is connected to the side bridge right here. So let's go ahead and click and create another manual contact region. Okay, and then let's select the edge of the road, which is a little bit difficult. All right, so let's go ahead and try that. Okay, so that's not what we wanted here. So you can see I tried to click this edge right here, but instead of giving me the edge of the road, it gave me the edge of the bridge. Okay, so you can kind of see, you kind of preview what part of the geometry is here on the right. Okay, and so let's go ahead and replace this. Let's go ahead and click cancel. That didn't do anything. Okay, and let's now select. Let's make sure we're selecting the edge of this road. Okay? And so we kind of have a benefit here because the road kind of overhangs a little bit right here. So let's go ahead and click that. And click that. Okay, and so you can now see on this top right here, you know, we're selecting this left edge of the road, which is what we want. Okay, and then now for the other part of it, let's select the other, you know, let's select the left side of the bridge. So let's go ahead and hit apply on that. Okay, and then now we have the road, the edge of the road is now successfully bonded with the side of the bridge. Okay, then let's go ahead and do that for the other side. Okay, let's make sure we're on edge selector. Select the edge of this road. Okay. Make sure that we have the right edge, and that's correct, so that's not on the bridge. Okay. And then let's go to plane selector, select this plane, and then hit apply. Okay. Okay. And so what we've done basically here is we basically told ANSYS that these parts of the geometry are basically, you know, mated together. So there's bolts or there's a weld that's connecting them. And so any motion that they have, they should do together, okay? And so when you're modifying the geometry as much as we did in Spaceclaim, you want to make sure that you have all of these, you know, connection regions and they're good, okay? Okay, and so now we're set to mesh it, okay? And so I'm not going to do anything special here, but the only thing I'm going to do is I'm going to change the size. And so I'm just going to apply a global size to this guy. So I'm just going to change that option right here. As you can see, the default mesh size here is 3.6694 inches. And so let me change this down to 1 inch. Okay. And then let's go ahead and produce this, this mesh. Okay. And so you can see here, we now have our mesh. And you can see that the mesh looks blocky, right? And so you're probably thinking, you know, what the heck? You know, what, we just went through all the trouble to turn this into shells and beams, but these don't look like shells and beams at all. Okay. So you know, luckily, I think this is simply just a rendering thing. So these are actually, you know, 1D and 2D elements. It's just that, you know, ANSYS kind of makes them look like they're in 3D. But you know, we went through all the trouble to make these into shells and beams. You know, but so you can kind of trust that it's shells and beams. Okay. Okay. And so of course, you know, you can play with the mesh size here. So you can see with the mesh size of 1 inch, we have 3,680 elements here. Okay, so we can actually make this smaller. So let's do 0.75. Okay. So go ahead and update the mesh. And now we have, oops, still meshing. Okay, so you can see that mesh looks a little bit better. And now we have 7,003 elements. Okay. And so this is the real power of doing shells and beam elements, because if we hadn't done this and we tried to mesh this with, you know, tetrahedrons and hexahedrons, you know, our element count would be ginormous here because we have so many thin and slender elements that we had to kind of, you know, mesh the crap out of it and pick a really small size. But because we're doing shells and beams here, you know, we can pick a relatively modest mesh size and still get kind of accurate results. Okay. Okay. And so let's go ahead and apply some boundary conditions on this just so we can, you know, run the simulation. So first thing I'm going to do is we need to fix support. We always need to fix support. So I'm going to fix this side of the road right here. Okay. Next, I'm going to insert a displacement support, right, just to make sure that our road isn't going to go anywhere. Okay. So I'm going to make it so that it can't displace in the y direction. So on the left-hand side, we have a fixed support. So that's kind of like, you know, remember that's restraining x, y displacements, in this case z, and also rotations. But on this side, I'm basically just putting a roller. So I'm basically just saying that only the y displacement, you know, can't be displaced there. Okay. Okay, and so in addition to that, let's put some forcing. So let me put a pressure force. Okay, I'm going to put this on top of the road. Okay, and let's give it a magnitude of 500 psi. Okay, and so that's kind of to simulate, you know, cars going over the road or something. Okay. Okay, and so let's go ahead and insert some result fields. Let's look at total deformation, and let's look at the von Mises stresses, the equivalent stress. Okay. All right, so let's go ahead and click solve, and then let's see what the simulation turns out to be. Okay. All right, so you can see here that our bridge is crumbling. So we're looking at the stress field right now. So let's look at the deformation field first. Okay. And so this is what the deformation field looks like. Right? So you can see here that the deformations are high in the regions between the beams. We can see at the locations of the beams, you know, the beams are supporting the structure. So we don't have as much displacement on the beam itself. But away from the beams, we kind of have this, you know, hot spot of displacement right here as a result of the pressure. Okay. If we look at the stresses, you know, we can see that we have a lot of stresses at the locations where the beam at the beam intersections. Okay. And so the stresses are high there. Where's the maximum stress? Maximum stress, so our maximum stress is here at the edges. Okay. Okay. And so the stresses that you're seeing here, you know, these measurements are going to be a lot more reliable than if you tried to mesh this with tets and hexes. Okay. Probably if you try to mesh this with tets and hexes, you'll probably see that the stresses are probably going to be not as high because again, you don't have any nodes on the interior. But since we're computing rotations in addition to displacements, you know, we can see that we have, you know, that these stress computations here are going to be more reliable than not. Okay. Okay. Any questions on this? Okay, let me try one more thing. So let me change the element order to quadratic. Okay, so before it was kind of auto, but let's see what happens when we change the shape functions to quadratic. Okay. Okay, so it's meshing again. Okay. Whoa, you can see once we change the quadratic here, you can see the number of nodes exploded quite a bit. Okay, so let's go ahead and click solve. Okay. All right, and so you can see once we change the quadratic, you know, the stresses actually change quite a bit. So if you remember, you know, the stresses before this was like 4.28 times 10 to the 6. You know, once we change the quadratic, the stresses increase quite a bit, right? And so actually probably what you saw there was a little bit of shear locking, right? And so we talked about that a little bit before, where if you use linear elements with a structural simulation, you know, your stresses and your displacements are going to be underestimated quite a bit. And so you can see here, once we switch to quadratic, then the results changed, you know, quite a bit. Okay? And so if just to kind of highlight this again, you know, let's kind of remember this, that the maximum displacement here was about 5.6385. And so let's change the mesh back to linear. Okay. So let's go ahead and update the mesh. Let's go ahead and solve. Okay, for the deformation field. All right, so the deformations actually didn't change all too much, but you can see that the stresses there's a huge difference there. So you can see the stresses when you use linear elements are severely underestimated by a factor of almost 4, or about 4. And so, you know, that's a huge difference in the stresses. So if you're computing stresses, you know, you want to really make sure that you use quadratic elements so that you get more accurate computations. Okay. All right, question. All right, question. So do we need any mesh refinement? So yeah, actually, you know, a good rule of thumb is for mesh refinement is to look at the areas where you have kind of high stress concentrations. And usually those are some good areas for mesh refinement. So if you look at this mesh right here, you can see that we have stress concentrations here and here at the edges of the domain. And so these are actually great areas for mesh refinement. So if you wanted to, you can go in and refine around here, and you would get an even more accurate computation for the stresses. So yeah, that's a good point. And mesh refinement here will be a lot easier because we're using shell and beam elements as opposed to tets and hexes. Yeah. All right. Any other questions on this activity here? Okay. So if there's no more questions, that's all I had planned for today. So I know we're not turning anything this in, but I definitely encourage you guys to give this a try because it's it's shell and beam elements are pretty important in industry because a lot of manufactured things or a lot of engineering devices are not big blocks of stuff. They're actually thin sheets or slender beams, mostly just to save on materials. So you'll use this tool a lot. So even though you're not turning in, you can definitely give it a try. And if you have questions on it, you can definitely let me know. Right? So a question in the chat is: can we still change the mesh to tets and hexes, or it isn't possible since we switched to 1D and 2D? Yeah. So if you want to try this with tets and hexes, you actually have to go back to the original geometry. So you would have to start a new project. And then just open up the geometry in this without doing any of the stuff in Spaceclaim. And then once you mesh that, then that'll be with tets and hexes. Yeah. So you can actually compare. So actually that might be something good for you to try at home, is to compare the mesh and compare your results when you did tets and hexes and then versus this stuff. Yeah. Extrapolating is probably a more dead end than interpolating. Yeah. Extrapolating is always more difficult than interpolating. That's for sure. Okay, so I'll stick around, since we do have a bit more time in the lecture. So if you have kind of individual questions on either this or you want some feedback on your project, I'll stick around for that. But if not, I'm not going to keep you guys. So I hope you guys have a good weekend. Definitely keep working on the project. If you have questions, shoot me an email. I'll try to get back to you as soon as I can. And then next week, we'll probably, if whatever questions people have on the project over the weekend, we'll cover that next week as well. And then probably we'll do some more ANSYS demonstrations just to kind of give you guys some exposure to some of the capabilities and features it has. Okay. So have a great weekend, everyone. Thanks for tuning in, and I'll see you guys next week.